Okay, well, so let's announce a lemma. Vitali's covering lemma. Okay, so let E in Rn measurable such that E is included in the union E R alpha, the balls of radius R alpha, centered in X alpha, um, okay, with the family of open balls B R alpha, X alpha, satisfying that the supreme alpha R alpha is equal to C naught less than infinity. Okay, so then there exists a subfamily. Okay, and the subfamily we will note it as BR J X J J. This subfamily is of this disjoint set and numerable. Okay, such that measure of E is less than equal than phi to the n, and the sum from j equals to 1 infinity. Oh, okay, so the measure will be j x j. Okay, okay, so this lemma is telling us that we can take a subfamily of disjoint and numerable balls, and that the sum of the measure of these balls multiplied by phi over n, phi to the n, it will be greater than the measure of E, that is a measurable set that is included in the union of all the balls. Okay. Okay, so I'm not going to prove it, but we are going to use it in the following theorem. Okay. Okay, so the next theorem is the Hardy-Littlewood theorem. Okay. So let p between 1 and infinity, then m recall that is the Hardy-Littlewood maximal function, okay, that we saw in the last video. And okay, so then m is a quasi-linear operator of type pp. Okay, okay, and that means that there exists a, let's say, CP such that the norm MF P is less than equal than CP norm FP. Okay. Okay, so we already knew that M is of type infinity infinity. So now what we're going to do is to show that M is of weak type, and weak type 1 1. Okay, and that is that exists a constant C1, such that for every f in L1, the supremum of lambdas greater than 0, m lambda mf is less than equal than C1 multiplied by the norm of F1. Once we prove this, and using Marcinkiewicz theorem, then we can prove this, because we will have that is of type 1 weak and infinity infinity, and we will have the hypothesis for the Marcinkiewicz theorem. Okay, so let's define the set E lambda f that are the x in Rn, such that m of f is greater than lambda for any lambda greater than 0. Okay, so if x is in E lambda f, then there exists a ball Brx centered in x, such that integral in Brx of f y dy is greater than lambda multiplied by the measure of Brx. Okay, so recall that if we could express m of f as a function, then we could have something like this, for example, and then lambda is put in as a limit somewhere, and then we will have that integral, it will be somehow greater than the measure of the ball multiplied by the lambda. Okay, so we have this, and we will also have that E lambda f is included in the union of the x in E lambda f, the union of the balls. Okay, so this is telling us that the x's that of E lambda f are included in the balls that of radius Rx that contains the x's. Okay, so this is just a sketch. Don't take this seriously, but it's just to understand what this inclusion is telling us. So then the Vitali covering lemma guarantees the existence of a countable disjoint subfamily. The subfamily is going to be of Brxj. This is a J. Xj, J as a positive integer, such that so the measure of the set E lambda f is less than equal. Okay, and now we use Vitali's covering lemma, 5 to the n and the infinite sum of j equal 1. Now I have Brxj, xj. Okay, and now we will use this less than equal than 5 to the n lambda. Okay, so we can put the lambda on the other side, and we have lambda to minus 1, infinite sum. Okay, and now we will have the integral in the ball of the absolute value of fy dy, okay, and now we will just say that this is less than equal than 5 to the n lambda to the minus 1 norm of f1, okay. So we obtain that the measure of E lambda f is less than equal than 5 to the n lambda to the minus 1 norm of f1, okay. And we wanted to know that the supremum of lambda is positive, lambda multiplied by mf is less than equal than a constant multiplied by the norm of f1. So just putting the lambda on the right side and taking the right constant, we obtain the result. Okay, so m is of weak type 1, and then by marking Sewicz theorem, we have that m is of type PV. That is what we wanted to know. Okay, so we can extend the estimates to a class of kernels. So let phi in L1 Rn is positive, okay, positive, non-increasing, radial, it depends of R. So let's say depends of the norm. When we say radial, R is equal to the norm of x, and let's say that this is in 0 infinity. So then supremum t positive phi t convolution fx is equal to the supremum of the integral Rn phi t minus 1 x minus y over tn fy dy, okay, and this is less than equal than norm of phi 1 m fx, okay. Okay, so I'm not going to prove it, but a sketch of the proof is that if you assume that phi is a simple function, and you can write it this way, okay, ak, the sum, okay, so if you assume that phi is a simple function, then phi convolution f will be equal to the sum of k, ak, brk, 0, 1 over brk, 0, okay, xbrk, and this will be convolution fx, and so it will be less than equal to the norm of 1 m fx. Here we're using that the norm of phi 1 is the sum of ak, brk, and so then if we can approximate phi by a sequence of simple functions, then if we pass to a limit, we can obtain the proposition, okay.